This is the second part of the walkthrough of the AQA 2018 A-level chemistry paper 1. Okay, so hydrochloric acid, question 5.1, is a strong acid. State the meaning of the term strong acid. All you have to say is complete dissociation or complete ionization. Right, 2.5, in an experiment, 10.35 of hydrochloric acid are added to 25 centimeters cubed of barium hydroxide solution. Calculate the pH of the solution that forms at 30 degrees C. Right, now what it is best to do here is to, rather than write a balanced equation between HCl and BaOH twice, is to write down the equation for hydrogen ions. So we've got H plus and OH minus ions, and they're obviously going to neutralize to form water. And what I would do is I put start moles here. After the reaction, final moles, and then we'll have final concentration. So we've got to fill in these gaps here, and that should give us the answer. Okay, so how many moles of H plus ions have we got? Well, we've got concentration times by the volume. Conc is 0.1 times 10.35 centimeters cubed, so that's 0.1 multiplied by 10.35 over 1,000. That is equal to 1 point, so put that in there, 1.035 times 10 to the minus 3. Right, now we have to do the moles of barium hydroxide before we can work out the moles of hydroxide ions. So moles of barium hydroxide, again it's concentration times volume, so it is 0.15 multiplied by 25 over 1,000. That is equal to 3.75 times 10 to the minus 3. Now the moles of OH minus is double that, because 1 mole of barium hydroxide contains 2 moles of hydroxide ions. So moles OH minus ions, double that, which double 3.75 gives you 7.5 times 10 to the minus 3. So I put that in there, 7.5 times 10 to the minus 3. We don't really care about the moles of water, so forget about that. Now we can see that the OH minus ions are in excess. So essentially all of the H plus ions are going to react, so they're going to go. And how many moles of OH minus we've got left over at the end? So we've got 7.5 times 10 to the minus 3 minus 1.035 times 10 to the minus 3. 1 mole of OH minus reacts 1 mole of H plus, and that gives us 6.465 times 10 to the minus 3 moles of OH minus ions. Right, now it's important here that we realize this is a number of moles of OH minus ion and not concentration. So to find the concentration, we've got to divide that by the volume. So the total volume at the end, well, we added 10 centimeters cubed of hydrochloric acid, and we added 25 of barium hydroxide solution. That's 35 centimeters cubed. So the final concentration then is equal to, divided by 35 centimeters cubed is 0.035 dm cubed. So that gives us 0.1829 mole per decimeter cubed. That's the OH minus ion concentration. How do we find out the H plus ion concentration? That, well, we've got to use Kw. Okay, so Kw is equal to H plus times OH minus. H plus concentration, Kw, and the value there is 1.47. Here we go, there. Times 10 to the minus 14. It's not 1 times 10 to the minus 14 because it's not 25 degrees C, it's 30 degrees C, divided by the, so hang on a minute, H plus is equal to Kw divided by OH minus, 1.47 times 10 to the minus 14 divided by 0.1829. That gives you an H plus ion concentration of 8.03 times 10 to the minus 14. Take the negative log of that to give you the pH, and the pH is equal to 13.09. That's our final answer. Okay. I'd say the most common mistake there would be to forget to divide by, to confuse moles here. This is the final moles with final concentration. You do have to divide by the total volume there to get the concentration of OH minus. Right. Okay. The pH of water. Next question is 6.92. Why is it neutral at that temperature? Because, well, the definition of neutral water is not strictly speaking pH 7. It's when you've got H plus ion concentration is equal to OH minus concentration. And of course, that is pH 7 at 298 Kelvin, but at other temperatures where the value of Kw changes, it's not always exactly 7. And the definition of neutral is H plus is equal to OH minus concentration. All right, first 5.4, an oxide that can react with water forms a solution of pH 2. Aluminium oxide is insoluble, so it's not that one. Sodium oxide obviously can give you sodium hydroxide solution of pH 14. Silicon dioxide is insoluble, SO2 dissolves to give you H2SO3 in water, which is actually a weak acid, so that's why it's going to pH 2. So that's the answer there. Okay. All right, so on to weak acids now. This is a fairly straightforward question. What is the acid dissociation constant for ethanoic acid? Well, it's going to be, so don't forget, we have our weak acid here. It's going to dissociate to give its conjugate base and H plus. And so the Kw is equal to the concentration of the conjugate base multiplied by the H plus divided by the concentration of the weak acid. Okay, now 5.6 is a buffer solution. Okay, so we have 0.025 moles of sodium ethanoate dissolved in 500 centimeters cubed, and okay, and for 0.07 moles of ethanoic acid. Okay, right, so let's work out the whenever we're working out a buffer concentration, we need to work out the ratio of the weak acid to the right. So let's work out the moles of the weak acid. Let's call this HA and let's call this A minus. The moles of HA, it tells us, is at the start, this is before we add any hydrochloric acid, moles of HA is equal to concentration times volume. So that's 0.07 times 0.5. That is equal to 0.035. The moles of A minus, they tell us, that's fairly straightforward. They tell us that you've got 0.025 of the A minus. And what we're going to do is we're going to add hydrochloric acid to that. So we're going to add H plus ions. So which of these two things reacts with H plus? And it's obviously the A minus. So I'm going to write down here again this start moles, final moles sort of thing. Okay, so I'm going to write A minus reacting with H plus to form HA. I'm going to write down the start moles. Right, now the start moles of A minus we've got is 0.025, and the start moles of HA is 0.035. What's the start moles of H plus? Well, we have to do here H plus moles is equal to conc times volume. So the concentration is 2 and the volume is 5 over 1000 dm cubed. So that is equal to 0.01 mole of H plus. That goes in there, 0.01. So final moles. Right, final moles. Right. The concentration of A minus is going to go down by 0.01. So that's going to go to 0.015. And HA is going to go up by 0.1. So that's going to go up to 0.045. Now, let's just rearrange this equation here to get H plus. You don't have to rearrange it first, but I prefer to before we put the numbers in. So if we rearrange that, we're going to get H plus is equal to Ka HA concentration over A minus. Now we have to be careful here because look, we've got not the concentration of A minus, we've got the number of moles of A minus, and the same with HA. So concentration is equal to moles over volume. So final conc, so that's going to be moles over volume. Now we're not actually going to, we don't know the volume. Actually, we do know the volume, it's 0.5 dm cubed. But we don't need to actually work it out because we're just going to call it V, and those V's will cancel out. So the concentration we'll say is 0.15 over V, and that's going to be 0.045 over V. Put those numbers into the red equation here for H plus. H plus concentration is equal to the Ka, so 1.76 times 10 to the minus 5, multiplied by the concentration of HA, which is 0.045 over V over 0.015 over V. Those V's are going to cancel out. And also, if you look at that expression, is actually going to that's going to come to 3. And that actually, that's important. That ratio of HA to A minus in a buffer is always about 1. When I say it's about 1, it can range from anything from about 0.1 up to about 10. In this case, it's about 3, which is kind of typical. H plus then, concentration, work that out. You get 5.28 times 10 to the minus 5. Take the negative log of it to get the pH. pH is equal to 4.28. So that's quite a difficult buffer question, that when you add a little bit of acid to it. Sometimes they get you to add a little bit of hydroxide down to it. It's a little bit more difficult than a regular calculation for buffer. Okay, so right, now let's move on to question 6. Okay, so it's about electro potentials. Okay. Right. Right, so here we've got 2 half cells. Now, unusually, they're both made of exactly the same thing. We've got copper electrode in a copper sulfate solution. The only difference is if you look at the concentration here, this is 1 mole per decimeter cubed. So this is going to actually give you the standard value. Of course, standard value is when you have a concentration of 1 mole per decimeter cubed. And this is not going to be the standard value because you have a different ion concentration. So we'll come back to that later. Right, explain how salt bridge provides an electrical connection. Right, you have to say, right, it allows ions to leave or enter from the salt bridge into the electrode solution. So current can flow because you have a movement of ions in the salt bridge. And it's there to complete the circuit. That's all you have to say there, really. Okay. The standard electrode potential, next question, for the copper system then is plus 0.34. Now, that means that is when you've only got a concentration of copper 2 plus ions of 1 mole per decimeter cubed, which of course you don't have on the left-hand side. It's not 1 mole per decimeter cubed. Right, so if we use this equation, E cell is equal to E right minus E left. Now the right-hand side one is the standard potential because that's 1 mole per decimeter cubed, and we don't know what E left is. So E left, so we've got to find out, rearrange. E left is going to be equal to E right minus E cell. So E right is the standard value plus 0.34. And the earlier in the question it says what was the voltage was plus 0.16 volts, so minus 0.16 volts. That's going to be equal to 0.18 volts. So you can see the lower, this leftover hand electron with a lower copper 2 plus concentration is more negative than the standard value, and we'll see why that is in a minute. Okay, so why doesn't it have an electrode potential of 0.34? This because we don't have the standard concentration of copper 2 plus ions is lower than the standard concentration. Right. Okay, here we go. Give the conventional representation for the cell in figure 2. So I've copied figure 2 again. So the thing to do is to put the salt bridge down the middle. So that's your dotted line. And E right is this one. Now the oxidized species always goes next to the salt bridge. So that's Cu2 plus. Then we're going to get a phase change of a solid line. So that's an aqueous solution. And the copper metal is a solid. Put that there. And it's the same on the other side again. The oxidized species next to the salt bridge. And then phase change and copper there. That's the standard representation. Okay, so now it says what happens when we allow when the voltmeter is replaced by a bulb, and so you let the current will flow. Okay, suggest how the copper 2 ions of the left-hand electrode changes when the bulb is alight. Well, if we look here, this is we've got plus 0.34 volts here, and we've only got we worked it out is plus 1.8 volts here. So this is more negative. So what's going to happen is electrons are going to flow that way around in the circuit. So if electrons have been given out by this left-hand electrode, what is happening there is we are getting copper metal is turning into copper 2 plus and giving out electrons. So what's going to happen to the concentration of copper ions as the current flows in the left-hand side? This is going to increase. And of course, on the other side, the exact opposite is going to happen. The concentration of the copper 2 plus ions is going to decrease there. And the electrons will flow around the circuit until the concentration of copper 2 plus ions on both sides is exactly the same. And then the current will stop flowing. Okay, so that's the second part of that. Give a reason why the EMF of the cell decreases to 0. Right, it's because the two copper 2 plus ion concentrations become the same. And so that when they do become the same, you've got no difference in voltage there. 0.34 and 0.18 are the same. Okay. Okay, so Anhydrous aluminium chloride reacts with water. A solution is formed that contains a complex aluminium ion and chloride ions. Let's write an equation for that. Okay, so we get AlCl3 solid. You're going to get chloride ions. And the aluminium complex you're going to get is, of course, Al forms 3+ ions. You're going to have 6 water molecules. It's going to be a 3+ on that. So we need to balance that. We need to have 3 chloride ions, and we're also going to need 6 water molecules in there to balance it. And we've got 0 charge on the left-hand side, 0 charge on the right-hand side. Given the equation to show how Z, so this complex ion, can act as a Bronsted-Lowry acid. Right, Bronsted-Lowry acids are proton donors, and this is, don't forget, this is quite acidic. This is a Bronsted-Lowry acid because of the polarizing, don't ask us that, but that's why, the polarizing nature of the aluminium 3+ ion and the water ligands. You've got a dated bond forming from the oxygen there to the aluminium, but this draws electrons out of the water molecule, which makes these bonds a little bit weaker, and they can break, and so H+ ions can be given away. All right, so let's show how it can act as a Bronsted-Lowry acid. So we've got H2O6, 3+. It's going to give away 1 H+, okay? And so what's going to be left over is AlH2O 5OH, and the charge on this complex now is not 3+, it is 2+. 2+. Okay, so describe 2 observations you'd make when excess of sodium carbonate solution is added to solution Y. So we've got this species here. Now this is an acid, and of course the carbonate ion is a base. It can accept 2 protons, and it will become carbon dioxide and water, so you're going to see fizzing. Don't forget, it's only the 3+ ion complexes that are strong enough acids to do this. The 2+ ones are not strong enough acids to do it, and you don't get CO2, you don't get fizzing, and so on. Okay, so observation 1 is you're going to get CO2 forming. The second observation is you're going to form this AlH2O. That's going to lose 3 protons to form that complex, which is not charged, and that's the white precipitate. So you're going to form a white precipitate. It asks for an equation, right? So now, if it asks for this equation, you've got to remember that, right? The aluminium ion, right down here, well, that's going to go to there, so that's losing 3 protons. The carbonate ion is only accepting 2 protons, so it'd be like the way you balance half equations for electrons. If you balance for protons, you times that one by 3 and times that one by 2 and add them together to get a balanced equation. So there we are going to get AlH2O 6 3+. We need 2 of those, and we need 3 carbonate ions. It's okay to leave the sodiums out there, they don't really do anything. So 3 carbonate ions. That's going to give us 2 of the aluminium complexes, which are uncharged. And we're going to get 3 carbon dioxide molecules, and we're also going to get 3 water molecules. So there's our balanced equation there. And if you want state symbols, that's aqueous. That's going to be a solid, a white solid. Okay. Right, aqueous potassium hydroxide is added in excess to solution Y. Okay. So solution Y, of course, is the aluminium hexaqua complex. Right. So first of all, what's going to happen is you're going to get it will get a white precipitate. And what's the equation there? Well, it's the aluminium losing 3 protons. So we're going to need 3 OH minus. Each one of those OH minus removes a proton, so we're going to get AlH2O 3 OH, and we'll get 3 waters coming off there, and that is a white precipitate. Now, if we had excess OH minus, then we remove a further proton from that, so it becomes negatively charged. Okay, so the second observation you're going to get, which I haven't really left space for, is the white precipitate. Observation 2 is the white precipitate dissolves. When you add excess. And the equation for that, I'll do it in yellow there. Right, we've got this white precipitate, H2O3, OH3. One more OH minus ion. It removes another proton to form, so you're going to end up with just 2 water ligands, 4 OH minus ligands, and the charge on that is going to be minus, and you'll get another water molecule, and this is soluble, so that's in solution. Right, now this question here, we've got a 6 marker, okay? So I'm not going to write an essay, I'll just write some bullet points here. So why is this? To explain why sodium bromide has a higher melting point than sodium, so we've got to think about sodium. Right, and then we need to compare that to sodium bromide, and finally we need to compare the sodium bromide to the sodium iodide. So let's just see what is the what is the structure and bonding of sodium. Well, sodium is a metal, so you're going to have a regular lattice of Na plus ions, and they're going to be surrounded by delocalized electrons. Right, so what's the attractive forces holding the solid sodium together, prevent it becoming a liquid or a gas? Well, it's the attraction of the Na plus ions to the delocalized electrons. That's not terribly strong, you might want to say, because sodium is actually quite a big ion, and it's only got a single positive charge in it compared to other transition metal ions. We're not asking you that, so don't go into that. But it's not, so sodium's got a fairly low melting point for a metal. Right, why have you got such a high melting point in sodium bromide? Well, sodium bromide is an ionic solid, so it exists as an ionic lattice. Strong electrostatic attractions, I would say. Between the Na plus ions, positive Na plus ions, and then negative Br minus ions. Final part of the question, why has sodium bromide got a higher melting point than sodium iodide? Well, it's due to the fact, right, you've got the sodium ion is the same in each case. There's the bromide ion. Right, on the same scale, the iodide ion is going to be bigger. All right, because the next one, okay, the iodide ion is bigger, so you can say the electron density, I would say, of the iodide ion is lower, so the attraction for the positive sodium ions is slightly weaker, and so the melting point is a little bit lower. I think you need to cover all of those points there to get 6 marks. So understanding ionic bonding and understanding metallic bonding, and understanding the factors which affect the strength of the ionic lattice, and that relates to the Born-Haber topic as well. Okay, it's all to do with charge density of the ions. Okay, right. Right, now this is just an ideal gas calculation. So you need the equation when sodium is added to water, okay, which is like a GCSE question, equation really, but sodium plus H2O gives you sodium hydroxide and a half H2 gas. Okay, so the important thing there is that 1 mole of sodium is going to give us half a mole of H2 gas. Let's work out our moles of sodium. That's going to be mass over mR. We've got 250 milligrams, so that's 0.25 grams over 23. That's 0.0186. These are numbers in the calculator. Right, it's 869 actually. Okay, so how many moles of H2 are we going to get then? It's going to be half of that. So that is 0.0543. Right, ideal gas equation. Right, PV is equal to nRT. And we just have to be really careful with the units here. So this is a volume, so rearrange, we get nRT over P. Now the volume is going to be in meters cubed. Okay, and it asks us for in centimeters cubed. We're going to do the conversion at the end there. Okay, so the volume in meters cubed is equal to the number of moles, so 0.0543, multiplied by the ideal gas constant, multiplied by the temperature, which is going to be in Kelvin. 25 degrees C, that's 298 Kelvin, so there's another thing to remember. And the pascals, the pressure has got to be in pascals, not in kilopascals. So we have to do 101 multiplied by 1,000. Okay, so put that into the calculator, and we get 1.33 times 10 to the minus 4 meters cubed. And there's always a confusion. How many centimeters cubed in meters cubed is a million. So multiplied by that, a million. It's not 1,000. It's 133 centimeters cubed to 3 sig figs. So really, ideal gas, you can't go wrong if you don't get confused with the units. Right, calculate the concentration in moles per decimeter cubed of the sodium ions in the solution produced in the reaction. Okay, so, right, concentration is equal to moles over volume. The number of moles of sodium ions we worked out was this. So that's 0.01086 divided by the volume, which is 0.5. And that is going to 500 centimeters cubed, of course, 0.5 dm cubed. So that's going to be the answer there is 0.0217 to 3 sig figs mole per decimeter cubed. That's question 8. All right, 8.4. Sodium reacts with ammonia to form the compound NaNH2 that contains the NH2 minus ion. Draw the shape of the NH2 ion. Now, whenever I draw this, I always like to draw a dot cross. Obviously, that's not the answer, so you just cross it out afterwards. But we've got, right, you've got nitrogen, and we've got 2 hydrogens there. Right, there's a covalent bond here, so we have a dot and a cross there, a dot and a cross. The nitrogen is in group 5, so it's got 5 of its own electrons, but because this is NH2 minus, it's got an extra one. It's got 6 altogether. We've only drawn 2, so it's got 4 more. So you've got 2 electrons there. If you like, that green one is the electron that's come from the sodium, the extra one. So what we've got is 2 bond pairs and 2 lone pairs there. So this is very similar to the shape of water. So what's going to happen there? Right, you're going to have a nitrogen, you're going to have, there's one, there's another one, and then you've got the, you've got the lone pairs here. Now, normally, if you've got 4 pairs of electrons, the bond angle there, like in methane, is going to be 109.5. But because you've got lone pairs, and 2 of them, and they repel more than bond pairs, the usual quoted value there is about 104.5 degrees. If you remember for ammonia, which has actually got NH3, sorry, which has got, that's 3 bond pairs and 1 lone pair, that's 107.5, the angle for that. For methane, which is 4 bond pairs, that's 109.5. And when you've got 2 bond pairs and 2 lone pairs like we've got here, and like you get in water, the bond angle is 104.5. So I think for the full marks there, you have to obviously say 2 bond pairs, 2 lone pairs. You have to say repulsion between lone pairs is greater than the repulsion between lone pair and bond pair, which in turn is greater than the repulsion between bond pairs. And I think it's also worth mentioning there, people sometimes don't because it's kind of obvious, but do mention it, say that the pairs of electrons want to get as far away from each other as possible. I would definitely say that. So it's question 9, all right? So it's about vanadium chemistry and electrode potentials. Okay, identify the species that can be used to reduce the dioxyvanadium ion there to the VO2 plus ion. All right, so we're going to need, which equation are we interested in here? We are interested in this one. And we want to be able to push this one forwards, okay? So in other words, we want to make it accept electrons. So we've got to get another one, which is better. It's better than this one at going backwards. In other words, if it's going backwards, it's got to be better at giving out electrons. In other words, it's got to be more negative. Now, unusually here, in this table here, they haven't put them in order for some bizarre reason. They nearly always put them in like most positive to the most negative, or the other way around, most negative, but they haven't done in this case. But the only one that is more negative than 1 volt, okay, is this one here, is the zinc. Right. Actually, also, if you look there, that could be used to reduce the, yeah, that is the zinc. Actually, the zinc will do it, and also the zinc can do it. This is also less negative. Fe2 plus can do it, and also V3 plus can do it. So there's actually 3 species there that can reduce it. Okay, but it says to no further, so I am not reading the question properly. Okay, so the trouble is, of course, right, if you use zinc, what can zinc do? Zinc can push that backwards to VO2 plus, but then it can make this one go to V3 plus. You can make that one go to V3 plus, and then it can also, okay, so the zinc would be no good, so you can't use that one. The iron would be no good either, because the iron could reduce it again. It could reduce this one there, and it could reduce it again to there. So iron would be no good. So the only one that could really do it then is the V3 plus ion. That one would reduce it. It would only reduce it 1 step, and it wouldn't reduce it any further. So the V3 plus ion is the answer there. And what I would say there is, in the explanation, I would say that the electrode potential of the of this one here, of VO2 plus V3, I would say that that is more negative, so it's less than the electrode potential of the VO2 plus. I'd say that, and you also need obviously you would probably need to say that Fe2 plus is not suitable. That is not suitable because that is also less negative than the than this one here, which is the VO2 to the V3. So the that is the species is V3 plus, the only one. Right, give the oxidation state of vanadium in VOH2O5 2+. Right. Right, so the charge on the species, the sum of the oxidation numbers is equal to the charge on the species. Well, what have we got there? We've got vanadium, which we don't, oxidation number, well, the charge on the species is +2. The vanadium, we don't know. We've got this oxygen, so that's -2. We've got these 5 oxygens here, so that's -10. And then we've got 10 hydrogens, so that's +10. So what's going to happen to those lot? They cancel out. So we get V -2 is equal to +2. So V is equal to +4. It's +4 oxidation state. Okay. Right, so we've got this complex ion with 4 water ligands and 2 chloride ligands. Okay. So that means that must actually be that this is in the +3 oxidation state here. It must be 3 plus that vanadium. Each chloride, of course, is 2Cl minus, and the overall charge is +1. Okay, one isomer is shown. Draw the structure of the other isomer and state the type of isomerism. Right, so here we've got the 2 chloride ions, and they are kind of next to each other. Or we could have them opposite each other. So let's have this chloride coming out, and this one, the other chloride, is opposite. So it's like a bond angle of 180 between those two. That would have to be a water. This one would have to be a water as well. This is a water, and that's a water. What kind of isomerism is it? Is stereo isomerism. And you may want to add it, so it's geometric isomerism, because it's not optical isomerism. The other kind of isomerism, stereo isomerism, of course, is geometric. Okay. Right, heating ammonium vanadate, this stuff here, okay, produces vanadium 5 oxide, water, and one other product. Like just to check, you can see that the oxidation number of vanadium there is +5, and it's +5 in vanadium 5 oxide, V2O5. So there's no redox involved here. Right, so we're going to get NH4VO3 goes to V2O5. So I'm going to have to double that there. Right, so that means the other product, we're going to get water, and the other product is obviously going to be ammonia. There's going to be no redox, so we're going to have 2 NH3s. And right, we've got one water molecule. And you just think you've got 6 oxygens on this side. You've got 2 times 3 is 6 there, and you only got 5 there, so you must have another one there. The hydrogens, right, you've got 6 H's there, and you've got 2 H's there, makes 8, and you've got 8 there, so that's the equation. Right, this question, 9.5, vanadium 5 oxide is catalyzed using the manufacture of sulfur trioxide, and this is a straightforward recall from the syllabus, and they always ask this, and they never seem to ask anything more sophisticated than this. All you have to show is that right, V2O5 is going to oxidize SO2 to SO3 and make vanadium 4 oxide in the process, and then the vanadium 4 oxide reacts with oxygen to regenerate it to turn it back into vanadium 5 oxide. So I just learned those 2 equations, and they very rarely ask anything else, but just to regurgitate those. Now, this last question, 7-mark titration, and it's a pretty challenging question. We'll see. As you say, it's so-called back titration, where you well, let's see why we call it back titration and what happens here. So it says, right, we've got to find out the water crystallization in sodium carbonate. So we first of all start off with a beaker of hydrochloric acid. And the concentration of that is 0.25 mole per decimeter cubed. And we have a volume of 200 centimeters cubed of that. So how many moles of hydrochloric acid have we got there? And I'm going to call that moles initial. Right, it's conc times volume. Concentration times volume. Which is 0.25 multiplied by 0.2, which is equal to 0.05 moles. That's the initial concentration, initial moles of HCl. What we're going to do then is we are going to add some sodium carbonate to that. We're going to add 627 milligrams, so that's 0.627 grams of sodium carbonate. Now, sodium carbonate reacts with hydrochloric acid, so that's going to use some up. All right, and so we're going to have here, and let's say this is the number of moles. Let's call that final. Let's call that moles HCl F. Okay, so a small amount of some of the initial moles here has been used up. We've got that many left, and we're going to subtract the final from the initial to work out how many moles of HCl have been used up. Before we do that, that is transferred to a volumetric flask, and it's make the volume up to 250 centimeters cubed. That's going to be HCl final in there still, even though it's diluted. The mole hasn't changed, even though we diluted it. And then in the titration, right, you take 25 of this out, so you take 1/10 of this out. So here's the titration. Here's our burette. And we're going to take 25 of that out. Put it into a conical flask. And we're going to titrate this against, so that's HCl. We're going to titrate it against NaOH. And the concentration of the NaOH is 0.15 mole per decimeter cubed. And the volume we require is 26.6 centimeters cubed. So what we're going to do is we are going to, just a brief overview, is we're going to find the moles of HCl. Well, we're going to find the moles of NaOH, concentration times volume here. From that, we can work out the moles of HCl. They react in a 1-to-1 ratio. I'll write the equation in a minute. Multiply it by 10. That's going to give us the moles in 250. That's HCl final. We know HCl initial here. we can work out how many moles, we'll call that HCl used up, and it's going to be used by the sodium carbonate. That's going to be HCl final minus HCl initial. So we can find out the moles used up. We know that 1 mole of sodium carbonate reacts with 2 moles of HCl, so we can work out how many moles of sodium carbonate we've got. That's where we're going. Okay, so let's do that first of all. So moles of NaOH in the titration is equal to conc times volume, 0.15 times 26.6. That is going to give 3.99 times 10 to the minus 3 moles. Now NaOH and HCl react in a 1-to-1 ratio. There's the equation. So I'm going to say, therefore, moles HCl in 25, that's in here, that's going to be the same. We want to work out the moles in 250 to give us HCl final, so we times that number by 10. So let's call it HCl, moles HCl final is equal to 3.99 times 10 to the minus 2. Right, now the moles used up by the sodium carbonate is initial minus final. So the initial moles was 0.05. Write that down. HCl initial minus HCl final, 0.05 minus 3.99 times 10 to the minus 2 is equal to 0.0101 moles. Okay, now that's used up by the sodium carbonate. Sodium carbonate reacts with hydrochloric acid in a 1-to-2 ratio. So you've got Na2CO3 plus 2HCl goes to 2 sodium chloride, CO2 and H2O. So therefore our moles of Na2CO3 is going to be equal to 0.0101 divided by 2, which is 5.05 times 10 to the minus 3. Okay, now we know that moles is equal to mass over mR. Right, we know the mass of sodium carbonate hydrated. So this is sodium carbonate dot XH2O. We know the mass hydrated. They told us that was 0.627. So that's at the start of the question. We've just worked out the moles there, so we can work out the MR. So let's do that. So the MR of sodium carbonate dot XH2O, rearrange that equation, we get MR is equal to mass over moles, 0.627 over 5.05 times 10 to the minus 3. That is equal to 124. Right. Now, if you add up this bit here of the MR, that comes to 106. So this bit here is going to be 124 minus 106, which is equal to more or less 18. So we can say we've got 1 molecule of water. So the value of X in this formula is equal to 1. Okay, that's the end of that paper.